Hi everyone, and thanks for joining me in this Interspeech 2020 presentation, in which I'm going to present our work in designing a voice type classifier for child-centered Daylong recordings. So, one method used by psycholinguists to study child language acquisition consists of putting a microphone in a child's vest to record the language environment of this particular child. Given this day-long recording, psycholinguists are facing different problems and challenges. For instance, they might want to answer the following questions. So when does someone speak? Who speaks to whom? How much speech is the child exposed to? So for this question, we can think in terms of duration or maybe in terms of number of words and so on. There might be other problems that psycholinguists are facing, for instance, how to measure the child's ability to perceive and to produce speech, or how to link the input that the child receives to the output the child produces. And all of these questions need to be answered on challenging and noisy day-long recordings, knowing that day-long recording can last up to 20 hours, and we can have multiple day-long recordings per child. And this is where speech processing people can play a big role by developing automatic tools to extract useful information from these day-long recordings. Um, a, a current system that is used by many researchers all around the world is called the Lina system. So with Lina, you can both record and analyze the data. You can extract useful information, such as the speaker turns, the number of words produced by another speaker, or the type of vocalization produced by the kid child. Is he crying? Is he laughing? Or is he babbling? Those kind of information. Um, the drawback with the Lina system is that it is proprietary, meaning that improving or extending its functionalities can be quite hard or even almost impossible. Even finding information about the way their algorithm work can be quite painful. So for our work, we focused on one of the earliest stage in the Lina pipeline, which consists of solving the voice detection task. So we want to be able to tell if a given frame has been produced by the key child, that means the child wearing the recording device, or if this frame has been produced by any other child in the environment, or by any male adult speaker or any female adult speaker. So in our paper, we compare our approach with its proprietary counterpart, the Lina system. So to develop our voice type classifier, we first had to gather multiple child-centered corpora. This gathering is called baby train in the table. It covers many different languages. So for instance, we have Greek, we have English, Japanese, Mandarin, French. We even have languages spoken by indigenous people, such as the Tsimane language or the Juhoan language. And the baby train corpora sums up to a total duration of 260 hours. We also keep a holdout data set on which we are going to compare our approach with the linear approach. So maybe I can play a few audio samples.
Um,
So in this one, you can hear the child.
Pete wanders along the river. He sees T-Rex. T-Rex plays guitar.
In this one, you have the mother telling a story.
Belly, 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 belly. Loosen on that belly. Belly, belly, belly. Oh!
And the father playing with his child. So now that the data have been presented, we can go to the problem statement. So the problem is quite simple. We have an input sequence referred as S in the slide. So this input sequence can represent handcrafted features such as MFCCs or learned features. And for each frame of the input sequence, we would like to return an output vector of scores. with one score for each of the class. And in our problem, we consider 5 classes that are the kid child class, the other child, the male class, the female class, and the speech class. Please note that the scores don't sum up to 1, as multiple classes can be activated at the same time. Concerning the architecture's choice, we decided to start from the waveform, which is fed to a syncnet network in charge of extracting the features. Then the features are fed to a stack of LSTM layers that are themselves followed by feed-forward layers before outputting the scores. And the whole network is trained to minimize the binary cross-entropy loss. For the evaluation metric, which shows the F measure between precision and recall. So I won't go over the formulas, but I would I would just say that those are functions of the duration of true positives, false positives, and false negatives. So before presenting the results, I would just like to make one iteration over the whole pipeline. The first stage consists of the training phase, in which the training data set is augmented in an online fashion using additive noise, and this noise is drawn randomly from the Muson noise database. So we train our model for n epochs to minimize the binary cross-entropy loss. Then comes the development phase. So in this phase, we take one model every 5 epochs, and for each of the class, we compute one threshold to minimize the F-score obtained on this particular class. And then we select the best model depending on the average F-score obtained across all of the 5 classes. Then comes the inference phase, in which the model is applied over overlapping successive windows, so that at instant t we have multiple scores that we average together, and then we apply the threshold computed in the development phase to decide whether a given class is activated or not. So here comes the results on the test set. So in this table, we compare a binary system in which 5 models have been trained separately on each of the 5 classes. So we compare the binary system to a system referred as a multi in the table, which consists of a model trained jointly on all of the 5 classes. So this table shows that the multitask system consistently outperforms the binary systems. We obtain around 77% F-score for the key child class, 25.6 for the other child class, 42 for the male class, 82 for the female class, 88 on the speech class. This leads to an average F-score of 63% on the test set. Then we compare our model with its proprietary counterpart, the Lina system. So we run this comparison on the holdout data set. That means data that have never been seen during the training, neither by Lina nor by our model. This way, we ensure that the comparison is as fair as possible. And we observe in this table that our model consistently outperforms Lina's predictions. We have an absolute difference in terms of F-score of 13.8% for the key child class, 4.7 for the other child class, 5.7 for the male class, 20.8 for the female class, 8.2 for the speech class. This leads to an absolute difference in terms of average F-score of 10.6%. Last, I would just like to say that our code has been made publicly available on Git, where you'll find easy to use pre-trained models. And I will just finish by saying that our voice type classifier is being used has been used already. So for instance, it's being used in an analysis of 8,000 hours of child-centered Daylong recordings for the seedling study. It has been used to develop a linguistic unit count estimator in the same manner that we developed our voice type classifier. And it is also being used in a linear-like approach for the acoustic analysis of classroom environments. And that's it for me. Thank you for your attention.